Good afternoon, everyone. I'm Xing Lin from Electronic Engineering Department at Tsinghua University, and it's my great pleasure and honor to present this lecture on behalf of Professor Aaron Ochkan from UCLA, who was my postdoctoral supervisor. Uh, this presentation topic is programmable light diffractions for information processing and computational imaging, which primarily focus on building the artificial intelligence with light through physical principles. So the research work was first published in Science in 2018. In this work, diffractive optical computing and diffractive network were proposed for constructing intelligent physical systems to perform mathematical computations. I mean, there are lots of mathematics behind it. The diffractive neural networks enables all optical inference at the speed of light using passive components. Can be designed to serve as new optical components with advanced capabilities for computational imaging, and it can establish new frameworks for large-scale optical inverse designs in optical computing systems. This shows the architectures of diffractive deep neural network, which you can think of it as equivalent fully collected electronic neural network. The simplicity of these architectures is that it only requires to stack the diffractive modulation layers, where the computations is performed at the speed of light when optical field propagates through, and intercollect diffractive layers, so that the detectors at the output plane can directly detect the calculated results. Each diffractive modulation layer comprises large numbers of diffractive modulation elements to perform large-scale optical computing, where each element acts as optical neurons with the size on the orders of even much smaller than the light wavelengths to modulate the light property. For example, here shows the phase modulations of the light. And it can be easily incorporate the optical nonlinearities activations to improve the performance. So the layer coefficients are trained through deep learning. And once fabricated, they perform all optical inference without any power consumption. Spend one time on this. On the left hand, I show, on the one hand, I show on the left, the network can be trained as a classification reflective network for handwriting digital recognition. By finding the detectors with the maximum intensity measurement, the categories of the input can be determined. On the other hand, also shown on the right, the network can be trained as imaging diffractive networks. The network basically acts as an autoencoder for images that construct the incident optical field at an optical plane. So as we can see that the architectures features passive layers with low power consumptions, which complete the task at speed of light and low latencies with in-memory computing paradigms, and it can be easily scaled up to have more layers or more neurons for more complex tasks. So based on the training models, the diffractive modulation layers are fabricated for classification, both classification networks and imaging networks using the 3D printed process. Here, a figure on the top shows that the phase modulation patterns trained for 2 classification networks, each consisting of 5 layers on the MList handwritten digital database and a fashion MList database. So the fashion MList database is basically consists of fashion products, respectively. So the figures on the right show the corresponding 3D printed classification networks with layer space of about 40 lambda. And the similarity lays 5-layer phase modulation patterns contributed for amplitude imaging tasks with layer space of approximate 5 lambda. The figure on the bottom shows the experimental setups operating under the terahertz wavelengths, which you can think of it as vector network analyzers for testing the 3D printed diffractive neural networks under continuous wavelength illumination at 0.4 terahertz. These setups comprise terahertz light source, diffractive networks, and diffractive, the terahertz detector. So by integrating large numbers of modulation eliminations for large-scale optical computing, our architectures, as far as we know, is the first optical computing systems that's capable of achieving optical classifications with high accuracies on the MLIS handwriting digital database, which basically includes 60,000 training images and 10,000 testing images, with 10 labels from 0 to 9. Specifically, the models is achieved about 92% blind testing accuracy using the mean square error loss functions, and about 98% blind testing accuracy using the cross entropy C loss functions during the training. So after fabricating the networks, one may observe the reduce of the testing accuracy to some extent, but it can be improved to approach the model's range accuracy through carefully engineering and account for the systematic errors and model deviations during the training. So here are the experimental results. The categories of input data digit can be identified by localizing the detector regions with maximum intensity. Another important feature of these architectures is that it can actually be employed to process high-dimensional light informations by encoding the input into different light dimensions. For the MLIS database, the grayscale images of the input object are encoded in the amplitude channels of the light and then feed into the classifier. For the fashion MLIS database, the input object, which belong to the 10 categories, as exemplified here, are set to encode into the phase channels of the light. The flexibilities in encoding the input signals expand the system applications across variety of scenarios, including the sensing, imaging, communications, and accelerators. So here's the experimental condition result for different input of fashion products. Since this is a complex optical field computing systems, even with linear diffractive modulation layers for complex field modulations in high-dimensional space, encoding the input object into the phase channels also generate the nonlinearities. This is because the phase components is mathematically. Good afternoon, everyone. I'm Xing Lin from Electronic Engineering Department at Tsinghua University, and it's my great pleasure and honor to present this lecture on behalf of Professor Adam Ochkan from UCLA, who was my postdoctoral supervisor. This presentation topic is programmable light diffractions for information processing and computational imaging, which primarily focus on building the artificial intelligence with light through physical principles. So the research work was first published in Science in 2018. In this work, diffractive optical computing and diffractive network were proposed for constructing intelligent physical systems to perform mathematical computations. I mean, there are lots of mathematics behind it. The diffractive neural networks enables optical inference at the speed of light using passive components. Can be designed to serve as new optical components with advanced capabilities for computational imaging, and it can establish new frameworks for large-scale optical inverse designs in optical computing systems. This shows the architectures of diffractive deep neural network, which you can think of it as equivalent fully collected electronic neural network. The simplicity of these architectures is that it only requires to stack the diffractive modulation layers where the computations is performed at the speed of light when optical field propagates through and intercollect diffractive layers, so that the detectors at the output plane can directly detect the calculated results. Each diffractive modulation layer comprises large numbers of diffractive modulation elements to perform large-scale optical computing, where each element acts as optical neurons with the size on the orders of even much smaller than the light wavelengths to modulate the light property. For example, here shows the phase modulations of the light. And it can be easily incorporate the optical nonlinearities activations to improve the performance. The layer coefficients are trained through deep learning, and once fabricated, they perform all optical inference without any power consumption. Spend more time on this. On the left hand, on the one hand, shown on the left, the network can be trained as a classification reflective network for handwritten digital recognition by finding the detectors with the maximum intensity measurement. The categories of the input can be determined. On the other hand, shown on the right, the network can be trained as imaging diffractive networks. The network basically acts as an autoencoder for images that construct the incident optical field at an output plane. So as we can see that the architecture features passive layers with low power consumptions, which complete the task at speed of light and low latencies with in-memory computing paradigms, and it can be easily scaled up to have more layers or more neurons for more complex tasks. So based on the training models, the diffractive modulation layers are fabricated for classification, both classification networks and imaging networks using the 3D printed process. Here, a figure on the top shows that the phase modulation patterns trained for 2 classification networks, each consisting of 5 layers on the MList handwritten digital database and a fashion MList database. The fashion MList database is basically consists of fashion products, respectively. So the figures on the right show the corresponding 3D printed classification networks with layer space of about 40 lambda. And the similarity lays 5-layer phase modulation patterns contributed for amplitude imaging tasks with layer space of approximate 5 lambda. The figure on the bottom shows the experimental setups operating under the terahertz wavelengths, which you can think of it as vector network analyzers for testing the 3D printed diffractive networks under continuous wavelengths illumination at 0.4 terahertz. These setups comprise terahertz light source, diffractive networks, and the terahertz detector. So by integrating large numbers of modulation eliminations for large-scale optical computing, our architectures, as far as we know, is the first optical computing systems that's capable of achieving optical classifications with high accuracies on the MList handwritten digital database, which basically includes 60,000 training images and 10,000 testing images, with 10 labels from 0 to 9. Specifically, the models is achieved about 92% blind testing accuracy using the mean square error loss functions, and about 98% blind testing accuracy using the cross entropy C loss functions during the training. So after fabricating the networks, one may observe the reduce of the testing accuracy to some extent, but it can be improved to approach the model's range accuracy through carefully engineering and account for the systematic errors and model deviations during the training. Here are the experimental results. The categories of input data digit can be identified by localizing the detector regions with maximum intensity. Another important feature of these architectures is that it can actually be employed to process high-dimensional light informations by encoding the input into different light dimensions. For the Emrys database, the grayscale images of the input object are encoded in the amplitude channels of the light and then feed into the classifier. For the fashion Emrys database, the input object, which belong to the 10 categories, as exemplified here, are set to encode into the phase channels of the light. The flexibilities in encoding the input signals expand the system applications across various of scenarios, including the sensing, imaging, communications, and accelerators. So here's the experimental recognition result for different input of fashion products. Since this is a complex optical field computing systems, even with linear diffractive modulation layers for complex field modulations in high-dimensional space, encoding the input object into the phase channels also generates the nonlinearities. This is because the phase components is mathematically represented by the complex exponential terms that basically performs the theoretical activation function. So during the detections, the complex optical field is also mapped into the intensity measurements, which applies the threshold to the phase components and further introduce the nonlinearity. So based on this phase encoding strategy, Professor Oscar's teams has recently also proposed to repeatedly encode the input data with diffractive layers during the training to generate the multiple nonlinearities for the input and improve the light performance. The diffractive neural network architectures can actually be designed to operate under different wavelengths for variety of applications. For example, it can be applied for the field of visual computing to process visual information by constructing either the coherent or incoherent systems. In conventional visual computing, visual information is first digitalized, followed by a series of image processing steps. With diffractive visual computing, visual input not need to be digitalized during the processing, which means that the phase, amplitude, polarizations, and the spectrum information of the object can be directly processed by diffractive networks and processed in analog domains before the digitalized. This implies that the complex visual information can be transformed into extracted visual representations without undergoing any preprocess. And image acquisitions on phase retrieval steps. And another characteristic of is that the physical size of the diffractive processors scale linearly with the size of the input field, making it well suitable for tasks requiring a larger field of view and high resolution. Building on these principles, it turns out that different types of application-specific systems can be developed to demonstrate the capabilities of these architectures in directly processing the optical field or electromagnetic field. One research work showed here is published in Nature Communications involved using the diffractive networks with phase layers with passive phase modulation layers for optical phase constructions. In these systems, it learns to reverse the optical wavefront. The input patterns and the different wavelengths are actually conjugated and mapped to the output planes, shown here, which means that it can be applied in environment environment aberration, corrections, time reverse focusing, and so on, without the need for nonlinear crystals using complex optical setups or electronics feedbacks using the conventional techniques. And here are some other systems developed in Professor Oscar's lab, especially for sensing applications. This network has been employed for The single pixels terahertz sensing to swiftly detect the hidden objects and diffractions. And also the distributed ensemble learning systems that have been developed to enhance network's performance. The unidirectional imaging systems that was also developed using the deep learning designed diffractive layers enables us to view an object from the one side while rendering it invisible from the other side. And these systems can also be applied to terahertz pulse shapings in the time domains, that preceding time domains, and can be also applied for optical quantitative face imaging to achieve face recovery, allowing us to directly image the transparent object. And the misalignment issues between the layers can also be resolved by training the misalignment resilience architecture. So MOS systems has been developed for computational reconstructions in optical domains without relies on the digital computers, including the freeze optical holographic reconstruction, real-time imaging through the random diffusers at the speed of light, classification-specific optical transformations, and secure data encryptions. And the snapshot multi-spectrum images, as well as the task-specific broadband optical systems for spectrum filtering and diffraction. And they enables the quantitative face images even through the random scattering medium. So together, these representative research works endeavors demonstrate the extended potential for the proposed architectures in computational imaging and reconstructions, sensing, and all other information, all optical information processes. So we will not go into details of all research works today, but instead highlight some of the research works in these presentations. First is about the computational imaging without a digital computer. Effective neural networks can see through random diffusers and scattering media at the speed of light, which has been long-standing challenges in optical field. Conventional imaging technology typically failed due to the strong scatterings and losses and the loss of the phase information during the measurement. In this approach, diffractive networks with passive and scalable layers is trained to optically reconstruct the target object obscured by the unknown unchanging diffusers, which means that the optical system itself can solve the task of underdetermined inverse problems. Here, the network is first trained on a digital computer to learn the task-specific models, and is then physically implemented through the passive face-only layers, with which the system can instantaneously reconstruct different input at the speed of light under different scattering conditions. We can see from the experimental results that for unknown new input object to the systems, the conventional lens fails to image the object. But the diffractive networks can instantaneously see through the static and dynamic random diffusers. So here demonstrate network settings, learning process, as well as generalization capabilities of the diffractive networks for different phase diffusers. The diverse set of phase diffusers were set into two groups. So one group is non-diffusers during the training, and another group is the new previous unseen diffusers used for testing. So during each training epochs, only a small set of known diffusers is utilized, enable the network to actually learn the distributions of diffusions without overfitting to the specific diffuser patterns. As we can see here, for the input object encoded in the amplitude domains in the testing database, the phase distortion introduced by the diffusers can be successfully corrected to reconstruct the input images using the learned networks, which works for both unknown diffusers patterns. These results reflect the key strengths of the approach. The learned physical structures is not just limited to a static environment, but instead show generalizations to unseen scaling conditions, enabling the practical employee in dynamic, unpredictable optical distortion environments. So with the working with length of 0.75 millimeter, result demonstrate system's high resolutions in resolve the input resolution chart grading patterns with a period size of 10.8 millimeter, which is about 14 lambdas, and 12 millimeter, which is about 16 lambdas. So the upper panels show the reconstruction results for resolving the resolution chart grading patterns for three known diffusers, K1, K2, and K3, and the three new unseen diffusers, B1, B2, and B3. The bar plot at the bottom present quantitative evaluations for different input grading patterns with period size of 7.2 millimeter, 8.4 millimeter, and 9.6 millimeters, 10.8 millimeters, and 12 millimeters. The horizontal axis basically indicates the ground truth period size of the input resolution target, while the vertical axis basically shows the period size measured by the system. Each color is corresponding to different numbers of training diffusers used in each epoch, range from the 1 to 20s. So the left plot shows the non-diffuser results of non-diffusers from the training set, and the right plot corresponding to the unseen diffusers. And the result demonstrates that the systems has learned the general physical transforms rather simply memorize the diffuser-specific mappings. Enable accuracy reconstructions of resolve the grading patterns with the resolutions to 10 lambda. So here are some results showing that demonstrating that the numbers of diffusers used in the training affects the reconstruction performance. Reconstruction quality is evaluated using the Pearson correlation coefficients (PCC) as shown the top, as shown on the right. Yeah. So the bar graph on the right indicates that as the numbers of diffusers per training epochs increase from like 1 to 10 and 15 to 20, means that the total numbers of diffusers used during the training rise. The PCC values of the reconstruction results improves. And here is the demonstrations of the experience systems. For phase-only modulation, layers of the diffractive networks were fabricated using the 3D prediction method. And these are the 4 layers diffractive networks. The input of objects were encoded in the amplitude channels, and the output planes, the reconstruction images appears optically, which means no further computation is needed with after light passing through the experiment the systems. And we can compare between the trained phase patterns obtained without the diffusers and with the diffusers. As we can see that the phase pattern is relatively in order without the diffusers. Well, in this works, see through the random scaling diffusers, the phase patterns establish greater disorders. So this page provides insight into the internal spatial structure of the trained diffractive networks, analyzing the distributed and alignment of the phase islands, which can be thought of as special channels across different layers. The top rows display the phase profiles of the 4 diffractive layers after training with 20 diffusions per epoch. We can observe that each layer features collections of smooth localized phase regions, which can refer to as phase islands that appears to form a spatial structure clusters. The second rows present the binary maps, highlighting that localization of the phase islands in each layers. These maps were generalized to isolate areas with significantly phase modulation activities. And the third laws illustrate pairwise overlapping between the consecutive layers. And the red region indicates where the phase islands from two layers spatially coexistent, suggest the alignment functions across different depths. And the bottom's image aggregates all four layers to show that the accumulations overlap across the entire stack. And this analyzes real net networks from a variety of spatial structures that reinforce each other's layer by layers rather than functions as isolated structures from within each layer. This research investigated how the interlayer space in diffractive neural networks influence its reconstruction performance under different diffusion patterns. Three configurations assessed with interlayers distance starting at 5 lambdas, 10 lambdas, 15 lambdas respectively. For each configurations, the top rows display the learned phase profiles across four diffractive layers. The columns on the right compare the network's output under three scenarios: low diffusers, long diffusers, and new unseen diffusers. The red numbers shown in the figures represent the calculated TCC values between the output and the ground truth. The layer space increase. The systems demonstrate improved robustness and high construction fidelities, particularly when generalized to new diffusers. And this enhancement is attributed to the greater space in solutions enabled by the increased propagation distance, which provides the networks with a larger design space with fully collected features to correct for the optical distortions. In contrast, the configurations with 5 lambda space exhibit limited performance under both known and unknown diffusers. And these results also offer the insight for design diffractive neural networks, indicating that not only the phase profiles, but also the geometrical configurations, such as propagation distance, play a critical role in determining the task accuracies and generalization. So far, the utilizing of diffractive neural network for imaging through both the known and unknown diffusers at the speed of light has demonstrated with robustness, generalizations, and low power consumptions, but without the requirements of electronic computing during inference. And the diffractive networks can actually be trained for other functionalities in visual computing. For example, the classification specific diffractive cameras. Unlike conventional imaging systems that aim to reproduce the fully visual systems, these networks are designed to selectively image only a certain image object, such as the object of interest in predefined categories, while not image the undesired object, to image or not to image application. Here are the results showing that the systems is trained so that the optical output planes reconstructs a meaningful image only if the input belonging to a target class. The input and the output are shown in the first row and the bottom rows. If the input come from the different class, the output remain blank and constructed. But if the input is belonging to the certain class, it will form the image on the optical plane. So these selective behaviors is implemented entirely in the optical domains, which introduce new types of building visual filters, offering the capabilities to decide whether or not to image based on the class level information before the light reaches the detector. To achieve the reliable class selective behaviors, the training of these diffractive cameras involves a carefully constructed loss functions shown here, which explicitly separate the response for positive and negative class. For the desired class, the positive loss functions facilitate the high fidelity reconstruction by using both the normalized mean square errors and the values of 1 minus Pearson coefficients, correlation coefficients. And for the undesired class, the network is paralyzed so that it will not generate output similarly to the ground truth on any patterns resembling positive examples. So this is enforced by adding the PCC-based penalties that discourage the overlapping between the negative input and both the true positive target and the shifted target. So through this training strategy, the networks learn to optically fill out, or you can say erase the non-target object, but preserve the target object. So the result is inherent selective optical systems where the class-specific logic are encoded into the base profiles of the diffractive layers. To illustrate the potential applications of class-specific diffractive cameras in privacy-aware sensing, consider these examples in secure screening scenarios. The monitors displays live videos streams which the specific individuals use, as in this case, the person wear uniforms are allowed to appear clearly in the images. For inspections, all other individuals are optically filtered out by the imaging systems before they are detected. So unlike conventional post-processing method that remove the data from acquisitions, this approach performs content-dependent class filter directly in the optical domains, meaning that the undesired content never forms a meaningful image on the scenes, on the sensor. Such architectures offer natural privacy protections, minimize the data volumes, and enhance the processing efficiency by embedded semantic filters into the front of the optical systems. So which means that it can go beyond the reconstructions and classifications. It can act as a content-aware visual gate for selective imaging, privacy-aware sensing, and a secure visual system. So here the simulation results show that evaluate the behaviors of class-specific diffractive cameras and the different network configurations and target classification definitions. So 3 test categories are shown. Parallel B's demonstrate the single class selective activities that preserves only the digit 5s on 7s respectively, while parallel C's shows that multiple class scenarios where 2, 5, 7 digits are retained. So for each categories, the top rows present the input digit followed by the reconstruction result from the 3 layers, and the 5 layers are diffractive networks, where we can see that the target digit are clearly preserved, non-target digit are strongly suppressed on completely filtered out in the output. The 5-layer network consistently produced better reconstruction contrast, confirmed that deeper optical networks can achieve more precise class filtering. So this result demonstrates that not only the system's capability of defines which class to preserve, but also flexibility to implement logic entirely in optical through learned diffractive network coefficients across multiple passive layers. So besides the AMLIS database, the system was also attached on a fashion AMLIS database, which contains more complex and text-rich object class. In these examples, networks was trained to retain all in lower body cloth atoms, suppress all other categories, including address, shoes, bags, and access. So the top row shows the presented input image, while the second row shows the output image from the 7 layers diffractive network. As seen on the left, object from the class of the interest are accurately preserved with high fidelities, while non-class target class on the right are optical field out are selectively degraded. These results confirm that the system's selectively imaging capabilities is not limited to the simple shapes digit recognitions. It can also be extended to more challenging real-world object categories, offering a flexible, scalable resolutions for both and visual filtering. Okay. Um, okay, so here presented the experimental results of the 3D printed class specific diffractive camera validating its so the experimental setups of class-specific diffractive cameras and the terahertz wavelengths of 0.75 millimeters for optical object filtering. So a continuous wave source illuminations the input objects which are placed in front of the diffractive camera, and the optical field passing through the diffractive layers. And the output signal is detected using the locking amplified synchronized with mixers and the amplifier chains. This setup enables selective coherent detectors of modulated terahertz signals. And the middle rows of the image illustrate misalignment resilience training strategies used to design the systems. And the diffractive camera consists of 3 layers, face-only layers, each optimized tolerance the vectorial shifting on angular deviation. The converged face profiles of layer 1, layer 2, and layer 3 are shown below. So real structures patterns response for class-specific imaging formations. The bottom row of the image shows the photos of the 3D printed and assembled diffractive system. So these are the presented experimental results of 3D printed class-specific diffractive camera, validating its capabilities to selectively image only object from the predefined class. In each blocks, here's the top rows shows displays the input test image followed by the corresponding numerical simulations and experimental output images obtained using the terahertz detector. For the target class, in this instance, the digit 2, both the simulations and experimental results exhibit clear image formulations, confirm that the class successfully reconstruct the desired object. In contrast, for the other digit object, field of views remains blank on diffuse, indicating that this non-class target input optical erase. The high consistencies between the simulations and experimental confirm that the accuracy of the optical designs and 3D applications both validate the feasibilities of using diffractive networks for performing class level filtering entirely in the optical domain. So following the experiment demonstration of class-specific diffractive images, this research works explore the broader concept from both class-specific optical transformers and encryptions using diffractive neural networks. As we can see, the networks is further implemented at a wavelength used in the silicon photonics, which is 1550 nanometers. In addition to the experiment result of reconstructing or erasing the image using the object categories as shown at the bottoms of the figures, the network can now be designed to carry out the different object operations depending on the class of the input. For example, it can be encode the data in a way that only encodables under the specific condition. So the result here shows that the approach can also be applied in the encryption. The network is trained to um, apply the unique intensity transformations to each object class, efficiently encrypt the input data into a class-dependent manner. In order to recover the original signals, a class-specific inverse optical transformers, which is denoted as the inverse of the transform of T, must be applied at the output to restore the input. Each class has its own corresponding decryption pathways. So different decryption pathways, meaning that only the corrected keys can be reconstructed the input for a given class. For a system level perspective, this allows n different users to code n different decryption key with each key is capable of unlocked only a single class of the optical data while keeping all other classes inaccessible. And this is achieved by incorporating the labels supervisions during the training process. Both encryptions and class conditions codings are directly integrated into the passive diffractive structures, expanding the potential application of the architectures in the secure communications and privacy preserved hardware. So the class-specific encryption frameworks can be further extended to include more categories. These results demonstrate that the possibilities of training neural networks for random class-specific intensity permutations. Each of the 10 data category classes from the quick-draws database is assigned unique permutation matrix, PM, and orange raw images can be recovered by applying the corresponding inverse transforms, PM inverse. So the blind testing results showing that the reconstruction corresponding to the inverse transform of transformations, PM inverse, so successfully only when the correct inverse is used, confirm that the network's capabilities to implement reliable class-dependent intensity-to-intensity mappings entirely in the optical domain. So besides the performed inference in optical modalities, there are additional representative works that highlights the synergistic between the digital neural networks and diffractive optical networks from the optical electronics computing systems. For example, the diffractive optical decoders are utilized to decode the representations generalized by electronics encoder, enabling the small resolution image display optically. Conversely, in the specific encoding single pixel machine vision systems, diffractive networks act as optical encoders that compress the optical object information into the spectrum signatures, which are then digitally decoded using the electronics neural networks. So similarly, the architectures can actually be utilized for optical communications through occlusions or random diffusions. The hybrid encoded decoding architectures can be designed either using the pair of the electronic encoders, optical decoders, or using the pairs of optical encoders and electronic decoders. So integrates of programmable interactions with the digital diffractive neural networks. So it's a metaphor about feeding data to introduce the ideas that the diffractive neural networks act as intelligent optical encoders with digital neural networks coders, supporting each other to enable hybrid optical electronic systems. All right, so for spectral encoding the single pixel machine visions, the goal is to perform the image classifications and other vision tasks using only a single pixel detector without forming a spatial images. In this framework, the diffractive networks is trained to decode the object-specific information into the spectrum domains, and then using the digital neural networks to decode the images. I combine the optical encoders encodings with the single pixels sensing sensitive detectors, systems can accomplish both the classification tasks and also the image reconstruction without requiring an image sensing arrays. This enables the development of the low-cost, complex, high-speed vision systems, particularly in wavelength image range where multiple pixel detectors are costly or even unavailable. The slides show the experimental validations of the spectrum encoding the single pixel vision systems operate under the terahertz wavelengths. The 3D printed broadband networks, diffractive network, consists of 3 phase modulation layers. It's visualized in the top of the image. The bottom numbers of the images illustrate the principles and physical arrangement of the systems, which is essentially a terahertz time domains spectrometers set up with a broadband pulse illuminations serving as the input to the systems. The spatial information of the input is transformed into a task-dependent spectral response, which is then measured by a single pixel detector, enabling the spatial inference to be performed through the spectral analysis of the modulated terahertz pulse. So here are the numerical and experimental validation of a single pixel optical classification using the broadband diffractive network. As we can see that the output spectral profiles are divided into 10 regions. So each corresponding to a categories of input digit. By finding the spectral bands with the largest signals, the classifications, the categories of the input digit can be determined. The networks generate 2 distinct output spectrum profiles for 2 input exemplar digits, 0 and 6. The model test accuracy on the test data sets of the Emily's database is 95.5%, with the confusion matrix showing on at the bottoms. The results further compared 3 different network designs, demonstrating that the network can actually make the trade-off between the numerical testing accuracies and the diffractive power efficiency at the output detectors, and achieve much high matches between the experimental and the numerical testing result. So here the improvement of the diffractive power efficiencies is about 1%. The model accuracy reduced to 84%, which can be improved to 91.3% with the collaborative designs of the image reconstruction electronic encoder. So the network's performance is also evaluated on the EM-list handwritten database, which comprises 26 categories of the letters. The top types of the diffractive networks were trained. Standard designs that encode categories using 26 distinct wavelengths. Different spectral encoders designs that use 52 wavelengths and performs pairwise spectrum subtractions to enhance the discriminations. As you can see that the non-differential networks achieve numerical testing accuracy of 84%, while the differential designs compare the relative spectrum intensity between the class pairs, further improve the performance to 85.6%. So after performing the all optical single pixel image classifications, which maps the spatial images onto the spectrum profiles, the super resolutions, super resolved image reconstruction modules can be further be incorporated. The reconstruction process employs a shallow electronic neural networks with 2 hidden layers to decode the spectrums and reconstruct the spatial images. In other words, the process begins with the input object, conduct the classifications based on the spectrum profiles obtained from the single pixel output of the diffractive networks, and then performs the image reconstruction from the measured spectrum profiles. As you can see from the result on the right, that both the numerical and experimental reconstructions exhibit high structural reconstruction fidelity. This framework illustrates the collaborative designs of the classification diffractive optical networks and image reconstructions, electronic decoders, and the feedback strategy are encoded. Both the networks is proposed to improve the accuracy of the classification networks, as shown here. The diffractive networks initially generate the spectrum profiles for the input, and the class is inferred by identifying the maximum spectral bands. Simplified samples such as the digit 0, 3 are correctly classified, as shown here, but the digit of 9 and 5 are misclassified. As you can see that these initial spectrum profiles are then fed into the electronic decoders, which reconstruct the images with high similarity to the original one. And then even the classification is incorrect. Then the digital reconstructed images is fed back to the diffractive networks, which generate a new set of spectral profiles that can correctly classify the 4 input digit. The training process can correct the misclassifications and allowing for the improvement in testing accuracy from 84% to 91% while preserving the energy efficiency. As mentioned earlier, the improved spectrum profiles can be further processed through the decoders to refine the reconstruction. This validated and integrated lightweight electronic decoders enable the self-consistent refinement and enhance the performance of the all optical classifications front end. Building on the single pixels spectrum encoders classifications frameworks, this works represent additional challenge performing all optical image classification through unknown diffuser, random diffusers. The figure on the left shows that the phase diffusers placed behind a random placed behind a handwritten input digit introduce a strong scattering distortion. The broadband diffractive networks is employed to transform the distortion wavefront into the spectrum profiles, which is then measured at a single pixel detector. The figure on the right illustrates that the different spectrum encoder strategies across 20 illumination wavelengths, enabling robust classifications by comparing the class-specific spectrum features. As we can see that even under the spheres image generations introduced by the random diffusers, which makes the conventional image almost impossible, by learning the distributions of the diffusion patterns, the diffractive networks can transform the distorted wavefront into a linear separable spectral signature so that it can be classified with the single detector. And this demonstrates the network's high tolerance to the optical distortions to the systems and enables optical classification under unpredicted distorted conditions. So the 4 confusion metrics shown here summarize the classification results of a single pixel broadband diffractive network under different diffusion conditions, including memorized diffusers using follow chained epochs, achieve classification accuracy about 82%. The forgotten diffusions used in early training epochs with a slightly lower accuracy about 89%. Entirely new diffusers that were never seen during the trainings, resulting in accuracy about 88%. And distortion-free input with low diffusers, resulting in accuracies of about 96%. So once again, the comparisons of the classifications and accuracies on the forgotten and the new diffusions further suggest that networks not only retains memories of the early retained diffusers, but also form statistical generalized models under the new different diffusion conditions. So another metaphor shows that the size using the optical front end to serve the digital back end, both the directions can be explored, including the reverse that it is involving the digital encoders feeding into the diffractive decoder. So following these ideas, the networks can actually learn the task of optical communications around the actually opaque occlusions. As we know that when opaque object block the direction path between the transceivers and the receivers. The traditional communication system fails. Here, with the hybrid optoelectronic learning architectures, electronic encoders and optical reflective decoders can be jointly trained to communicate optical information around the arbitrary opaque obstacles. As illustrated here, even when the input object is blocked from the field of view to the large extent, the reflective decoder is able to reconstruct the transmitted deformations by leveraging the remains of the optical field. We can see that the decoder process is fully optical, requires no computations at the receiver end. So here's the full architectures of the proposed diffractive optical communications. The image on the top depicts the diffractive neural networks encoded and diffractive electronic neural networks encoded and diffractive neural networks decoders, optical decoders are jointly trained to transmit optical information around the fully opaque occlusions. For each input message, such as an image, the encoders generate the class to the phase modulation patterns, which is now applied to modulated planar waves at the transmitter side. The generated phase encoded phase wavefront propagated through the environment, which is partially blocked by the random shaped opaque object. And this means that on the receiver side, the wavefront is processed entirely in the optical domains by the diffractive decoder, which reconstructs the transmitted image on the optical field of view. The images in the middle rows shows the structures of the fair standard convolution neural networks used for decoding, and the image on the bottom rows illustrate the physical configurations and the results used of using 3-layer diffractive decoders to process the encoded information around the occlusions. In contrast, the conventional lens imaging systems fail to, in this task, demonstrate the effectiveness of this approach, enabling more robust adaptive optical communication channels. So the architecture is further evaluated under the dynamic opaque occlusions. As you can see, that the different input targets actually encoded by the electronic neural networks to generate the encoded optical wavefront. Optical wavefront is propagated through the dynamics and opaque occlusions, and then through 3 layers diffractive decoders to construct the object, as shown here in the comparison to the conventional lens imaging method. The result further shows that even with significantly larger occlusions comparable to the field of view, the diffractive decoder still reconstruct the digit, while lens imaging fails completely in this task, as shown here. The encoder-decoder pairs adapted to the obscure structures and maintain effective communication. This slide shows the diffractive efficiency, calculated as the ratios of the optical powers at the output planes to the optical powers at the input apertures. This is utilized to evaluate the energy efficiency of the systems. As expected, the results reveals that the diffractive efficiency decreases with the increased occlusion width. Moreover, the diffractive efficiency actually relatively low, which is below around 1% even for a small occlusions. This issue can be addressed at the design stage by adding terms to the training loss functions. New terms is weighted the weighted loss with the weight of inter that penetrates the low diffraction efficiency. The result showing here is that by increasing the value of inters from 0.01 to 0.1, the diffractive efficiency can substantially improve from 0.67 to 52.5%. with a certain trade-off the reconstruction qualities within acceptable range, which is also evaluated with the SSM shown here. So and experimental setups used to evaluate the proposed optical communication systems around the opaque occlusions under the terahertz wavelength with the phase modulated encoding object, amplitude encoding square occlusions, and single layers diffraction coders demonstrated here. There are some of the experimental results. Despite the occlusions that block the large part of the field of views of the input images, the diffractive decoders is still able to decode and recover the structures of the input object with simulations, and experimental result shown here. So here's simulations and the experimental result. Yeah, some additional experimental results for optical communications around the circulars and irregulated occlusions, as mentioned before. So this is the occlusion one, and this is the larger occlusions within regular boundaries. This is the simulation result, experimental result. So let's wrap up the main content of the presentation today. It's main focus on the diffractive optical computing and diffractive neural networks developed by Professor Osman's lab since 2018. Now we can understand the concept of the conducting optical neural networks inference at the speed of light using passive 3D printed diffractive modulations layers with a variety of evaluation methods. The diffractive deep neural networks has facilitated a wide range of applications, including classifications, religions, encryptions, optical sensing, and communications. You may ask whether the architecture is diffractive limited. It turns out that the architecture can be extended to achieve the information processing beyond the diffraction limit. So after I run my own lab at Tsinghua University, the super resolution diffractive neural networks SDN is proposed for optical diffractive of arrival estimations with high bandwidth and low latencies, where the angular resolutions can achieve beyond the diffraction limit. So here, optical means that the wireless information is directly processed by using the carrier waves of the electromagnetic radiations as the computing media. As you can see, that the concept here is that the systems can estimate the angles of the objects, such as the base stations and the users, and perform the beamformings to establish the communication links between them. So it can be realized with spatial multiplexing or on temporal multiplexing to achieve large field of views with high resolutions for like sensing and optical communications.